All right, guys, welcome back. So I wanted to spend a few minutes just going over a couple of conceptual questions from the textbook. And these are both in your textbook. It's page 218, and it's question number 9, and it's also question number 13. I think there's some other great questions in here that you should think about being able to answer, but I wanted to focus in on these two for our conversation for today. So the first one, number 9, says, why do tightrope walkers carry a long, narrow beam? So there's a picture in your textbook. It's not this picture, but it's a similar idea. A lot of times when you see tightrope walkers, you'll see them carrying this very long pole. And I remember there being an exhibit at the Franklin Institute that had something like this. It was like all about circus physics and stuff like that. And they had one of these. And you might be wondering, like, well, what's the deal with that? What does that do? Think about it like this. By carrying that pole, and it's pretty heavy, and it's very long. So by carrying this long pole, what they're doing is they're putting a lot of mass far away from the axis of rotation. Really, if you think about it, rotation axis for them would be their feet, because if they tipped over, it'd be like they're rotating around the tightrope. Essentially, obviously they'd fall off, but that would be the axis of rotation. So by putting a lot of mass far away from the axis of rotation, you actually increase the rotational inertia. So what does that mean? That means it's a lot harder to rotate. So it makes it so that the tightrope walker is harder to tip over. Literally, it's more difficult for them to start rotating and falling off balance because of that. Just think about, like, without the long pole, when you're walking or something and all of a sudden you lose your balance. One of our natural instincts when we lose our balance is to kind of put our arms out to balance ourselves. Part of the reason for that is your brain kind of understands intuitively that by putting your arms out, you increase your inertia. You make it harder to fall over. So that the long pole is actually doing that on a much more magnified scale. It's a lot heavier and it's a lot longer, so it increases the rotational inertia even more. Not only that, but in addition to making them harder to tip over, it also makes it so that if they do start to tip, we're going to talk more about this later in the week, next week, if they do start to tip over, they're going to do it more gradually because they have more inertia. It's going to happen more slowly. So they have more time to adjust their balance before it goes back to normal. So that's the main reasons for this. It's pretty cool. Okay, and then 13 is the next question. And 13 says, a sphere and a cylinder have the same radius and the same mass. They start from rest at the top of an incline. Which reaches the bottom first? Which has the greater speed at the bottom? Which has the greater total kinetic energy at the bottom? And which has the greater rotational kinetic energy? Okay, so you saw in my notes from a couple days ago, picture that kind of looks like this. So what we know from the lab and some of the other stuff we did is that a sphere has the least rotational inertia of any like solid shape. Then it's a solid cylinder, and then it starts to go into like the more hollow stuff, because stuff that is hollow has its mass concentrated towards the outside. It's going to have more inertia. So if we release them both from rest and let them roll down the hill, the sphere is going to be faster down the hill than the cylinder will. Not by a lot, but it will beat it down the hill. And then it says, which has the greater speed at the bottom? Well, the one that got there faster. So the sphere would definitely be going a faster rate. Okay. Which has the greater total kinetic energy at the bottom? This is a tricky question. The answer is neither here. Think about it. They both started at the same height at the top of the hill from rest, and they both have the same mass. They're going to turn all of their potential energy into kinetic energy at the bottom. Now, it's going to be a combination of rotational and translational. And that combination will be different for the sphere than the cylinder. But if you add the two numbers together, the total amount of kinetic energy is equal to the total amount of potential energy that you had at the top. So they're going to have the same total kinetic energy. And then the last part of the question says, which has the greater rotational kinetic energy? All right, well, we've already established that if they roll down the hill, the sphere will win. So think about what that means. It tells us that the sphere has more translational velocity and therefore more translational kinetic energy. But they both started with the same potential energy. So if they both start with the same potential energy and one has more translational, then the other one must have more rotational. So in this case, the cylinder is going to have more rotational kinetic energy, and the sphere is going to be the one with more translational kinetic energy out of the two. We're going to see numerical problems like this. We're going to look at examples of being able to calculate this sort of thing, and look at the speeds at the bottom later on. But for now, I wanted you to just kind of pick it apart conceptually and understand, all right, when something has more inertia, it's going to take more energy to rotate. That's going to mean it's going to have less available for the translational motion. All right, see you guys next time.